There we go. Yay! I was warned a little bit that the light is sometimes a little bit flaky. So, okay. All right. Well, thank you guys so much for staying with me through a very, very long 2 days. I really, really appreciate it, and I hope you think it was a weekend well spent. We have just a couple more things to talk about before, and I do want to get to a nice closure. I do want to get to a nice stopping point, or resting point, not a stopping point, but a resting point. And I want to finish up a little bit of what we were doing last time with the low-pass filter, with the RC circuit. I want to take a quick digression away from that to look at filtering in general, and then we'll circle back and we'll do a Bode plot of that device. Then hopefully I can wrap that up in just about 10 minutes or so, and then we're going to get into mixers or multipliers. And remember I told you that there was a convolution property and there was also the modulation property. And so I want to talk about the modulation property. And just so your point of reference, that'll get us into the early sections of Lati in Chapter 4. Okay? That'll get us into the early sections of Lati in Chapter 4. And also, not quite, but pretty okay close to where we're going to forming the material for our first test. Maybe one more lecture, maybe two more lectures, but that's about it. So just so you have, I don't want to harp on that, but I want to give you guidance on it, just so you know where we're coming from in the bigger picture of the course. Okay. I'll start with this slide because this is actually a good place, a good run up to where we want to be for this filtering discussion. A filter will change the amplitude of certain frequencies relative to the others, and it will shift the phase of certain frequencies relative to others. Okay? And as we pointed out, what that implies is that there's a real part to the filter response and an imaginary part to the filter response. Okay? So remember, if we're looking at amplitude and phase, two pieces of information, a real part and an imaginary part, two pieces of information, not one-to-one, of course, right? Because you have to do real part squared plus the imaginary part squared to get the magnitude, and then you have to do the inverse tangent to get the phase. But two pieces of information, the bookkeeping at least works out. Okay? Now, let me motivate that, or let me motivate the math by drawing a y and an x, a magnitude r, and an angle theta. So if we were talking about geometry, we'd be talking about a Cartesian system, x and y, and we'd be talking about a polar system, r and theta, if this were geometry. Okay? And if it were geometry, we would say that the theta, the angle, was the inverse tangent of the rise over the run, this versus this, okay, hypotenuse and so on. And in our world, that's the phase. Okay. The magnitude, or the length of this vector here, in terms of the x and the y, is equal, and we've done this, is equal to the x squared plus the y squared square rooted. Okay. So now if I take a look at x of omega, h of omega, and y of omega, and I think back to what I've learned about the signals and systems, that we're going to have a real part and an imaginary part for my signals, and a real part and imaginary part for my system, and a real part and imaginary part for my outputs. Then I'm going to write x of omega is going to have a real part of x of omega and an imaginary part of x of omega. No great rocket science there, just a little bit of bookkeeping. X of omega magnitude is equal to the square root of that real part squared plus the imaginary part squared and the theta, and I'll label that as the phase of the x, is equal to the inverse tangent of the imaginary part of x of omega divided by the real part of x of omega. And so this is Cartesian representation. Then the polar representation of that signal looks like that. So this is what you're going to get out of the Fourier transform more than likely, because at e to the I omega t kernel will break up into a real part and an imaginary part. And this might be a more useful way of thinking about it. And the reason for that is that if I write y of omega is equal to x of omega multiplied by h of omega, what I'm really writing is that this is equal to x of omega magnitude, e to the I phase shift of x, phase function of x, and then h of omega is the magnitude of h of omega in polar form times the phase function of h of omega. And this is equal to the magnitude of y of omega multiplied by the overall phase response or phase function of y of omega. Okay? Nothing fancy here, right? I'm just writing this expression in terms of in terms of polar form. But what this tells me is two things. Y of omega magnitude is equal to x of omega magnitude multiplied by h of omega magnitude. And phi y of omega is equal to phi x of omega plus phi h of omega. Because of the rules of the exponent? Because of the rules of the exponent? The phases add and the magnitudes multiply. And this forms the basis for the Bode plot. Okay. And to draw the Bode plot, I want to look at a large number of frequencies and so I'll draw the axis here as the log of omega RC. So for our low-pass filter that we just talked about at the end of the last section, the low-pass filter for we just talked about at the end of the last section, we had the omega RC. Now let me actually go back a second and hold on 1 nanosecond here. Yeah, let me go back here for just a second. And I had, and that C is sort of questionable in there. So this piece here is my H of omega. That piece there is my H of omega. And I don't like the complex denominator. So I multiply by complex conjugates. Sorry, that should be a minus sign. I multiply by complex denominators to clear that out. And now you'll notice that this is my real part, and this is my imaginary part of what we did before. Okay? So, H of omega is equal to the denominator, and the numerator is the RC and I think that should be square rooted. So I take that squared, I take that squared, I put them together, I factor out at RC, and there we have it. Should double check that. That doesn't look quite right to me, but. And then the phase response is equal to the inverse tangent of omega RC, R squared C squared over RC, which is the inverse tangent of omega RC. And the important thing to notice then is that all the omegas come in units of omega RC. Okay? So if I'm picking my axis, I can normalize my axis to the log of omega RC. So the omega RC is there because of the natural relationship of the transfer functions, and the omega gets normalized, dimensionless units, to the RC. Okay, 1 over seconds multiplied by seconds, and then the log allows me to express a very large range of frequencies in a reasonable manner. And so on. So I picked the log here just because I like to have many, many, many decades of frequency to plot. And I'm going to use the same axis on the top graph and the bottom graph. I draw two graphs with the same x-axis. Now, the vertical axis here is going to be in dB. And because I'm worrying about the voltage, it's 20 log of the voltage. And so the units here are dB. And the maximum in this passive system is going to be 0 dB. No change in the signal. I like dBs in the vertical axis because they add. Instead of multiplying together, they add, and adding is easier to do than multiplication in your head. dB is a very common unit, although I don't know how common it really is for you guys to work with dBs. You've probably been introduced to them. My view is, 10 dB is an order of magnitude, 3 dB is a half. Okay? And then there's many flavors of dBs, dBms, and so on. Little d, capital B, capital D, capital B. If you take a look, the IEEE has probably 50 different dBs out there. I kid you not. But dB little m is reference to a millivolt, milliwatt. A dB MV is measured to a millivolt. Regardless, we'll be sloppy and just consider 20 log like that. In our transfer function, the turning point is at omega RC. And so that's where the 1 is. So if I want to be sloppy about this, I have a graph that looks like this, where this slope, I think, if I remember right, is 10 dB per decade. Things don't always cut off that sharply. There's a little slop in there, and the amount of that slop for this is 3 dB. Half, and then the slope, rejection slope. First order filter, 10 dB per decade. Higher order filters can get you faster rejections. Okay, that's good. Okay. All right. Now, as I pointed out before, there's a phase response. 0, minus pi over 4, minus pi over 2, 90 degrees. And the swing happens, there's no phase shift for low frequencies. The rejection from the filter is caused by a destructive interference, or 90 degrees out of phase. And the transition point again happens right around the pole location, or the omega RC, equal to 1. Okay? And then this guy will just flatten out asymptotically all the way out. Okay? So now if I have my signal response, I can overlay it on that to get my output. And if I have my signal phase response, I can overlay it on that to get my phase, override my phase of my output, in accordance with that transformation. Okay? So that's just a quick review of Bode plots that ties up the low-pass filter that we obsessed about last time, and buttoned it up. I caution you, there's still some rough edges in that, some sloppiness, the 1 over C being one of them, things of that nature, but the general idea is sound in there. Okay? Now, as far as I'm concerned, that takes care of chapters 2 and 3, our review of signals and systems. And what I'd like to do now is go back to that modulation property, and in the context of communications, I want to look at that. I want to look at that element a lot more. So what I want to do is I want to look at two signals coming together. I want to look at two signals coming together into a multiplier, into a modulator. And naively, if that little box or that little circle tells me to multiply those signals together, then I have an x1 and I have an x2 and I have an x1 multiplied by x2. Is that a linear transformation or a nonlinear transformation?
No.
How do you know that?
X2 isn't a constant. You don't have each and every value of x1 being multiplied with the same value.
Others? How do I know that that's not? Does anyone think it's a linear operation? If you had to go and say why it was nonlinear, what would you say? Don't flounder. Think back to what we've done in the past.
Because we need this community section. Because like say X would be a polynomial, not straight.
Okay.
Thinking in terms of linearity, if you take x1 of, let's say, 0, and add the x2 of 0, it would not be the same. Sorry, I think here just.
Well, let's try something. Okay.
Sorry.
Well, let's try something. Supposing I have x1. Supposing I have this guy here, and then supposing I have a y1 of t and an x2 of t, and so then this is y1 of t, x2 of t, right? So now if I have x1 plus y1, oh, I don't like that idea. Hold on one second. Let me start over here. Modulation. x1 of t, x2 of t, x1, x2. Okay. Now, the reason I don't think this is a linear transformation is you have a certain frequency content here, and you have a certain frequency content here. And when you multiply those guys together, you create cross terms. And what those cross terms mean by trig identity is new frequency components. Okay? New frequency components are generated by that modulation property. And that's hugely, hugely useful in the context of communications. Okay? That's hugely useful in the context of communications. Is to leverage, is to generate new frequency contents and to do so in a manner that makes our life easier. Can you imagine if I had to be a broadcaster on a radio station, and I had to reach the entire Dallas-Fort Worth area? If I couldn't modulate my signal into the kilohertz range, into the megahertz range, I'd have to shout really, really loud to reach all my listeners. And I probably wouldn't be able to do it, don't you think? So if I have my message signal, and I'm able to imprint it or mix it or modulate it or collide it with the carrier frequency of the radio station, then all of a sudden I'm not at baseband anymore. I'm not at the 2 kilohertz of my speech. I'm now at hundreds of kilohertz. and hundreds of kilohertz propagates like an electromagnetic wave. And it dances right through the atmosphere, easy as can be, with relatively low loss, other than the smearing out of the area that it covers, which is good, which is a good thing, because I'm reaching more users in all directions. And so this capability, this modulation capability, generates new frequency components, and that can be a very, very, very good thing for our communications. Okay? Now, to be specific about this, we don't generally have an arbitrary signal on one of our branches. What we generally have is a carrier signal, a cosine. And so this is cosine omega subcarrier t. And we generally have our message signal here. Okay? And then we multiply. And we get an m of t cosine of omega ct floating out that way. Now, let's explore these new frequency contents that we think we have. What does that look like in the frequency domain? That's the question that I want to play around with here. Now, the message signal M of t of my communication system. As I pointed out in the past, that's a fairly random signal. If you know what I'm going to broadcast, it's no new information. If I'm reporting the sports scores, you're listening because you don't know who won the game. And so you can't predict exactly what I'm going to say. So you don't know very much about M of t. Okay? And yet I want to know something about M of t times cosine omega ct. Okay, that's the output of my modulator. It's the output of my mixer. The mixing of one piece of information with another piece. But I know something about M of omega. I know if M of t exists, it exists as a voltage stream. Therefore, I know that it has a Fourier transform. Okay? I know how to calculate. Well, I may not know how to calculate that specifically, but in principle, I know that it has one. And I know that I actually know more about M of omega than I do about M of t. In other words, for voice, I know that M of omega occurs only for say up to 2 kilohertz. If it's music, maybe up to 20, 30 kilohertz. Okay? If it's video, maybe 30 megahertz. Okay? So I know something about the frequency content of M of omega, even though I know nothing about the details of M of t. Which is another motivation for why we want to think about what's going on here in the frequency domain, because I know something about that. And so what I'll do is I'll draw, and you'll see this 1,000,003 times. I generally use the same kind of distribution. Here's my picture for a distribution of frequencies in my frequency domain. the bandwidth of the filter is about, the bandwidth of the signal is, let's call that 2 pi b. Okay? And so if this were voice, 2 pi b would be 2 pi times 2 kilohertz or 3 kilohertz, depending on where I'm drawing the line. Okay? So this little hump here, this little hill is arbitrary. It just says that my speech more or less is at one or more tone of voice. Sometimes it drifts down, sometimes it drifts up. Okay? That's all I can really say. So if I know that, then the output of my mixer is the product of that times a cosine. And I know something about a cosine. So what I want to do is I want to take the Fourier transform of that. So what does this Fourier transform into?
We're going to transform into convolution of n over omega.
Yep. But the other thing I could do is I can just do the Fourier transform of that product and see what it looks like. I mean, you have to fish around, and you have to see which one of your techniques is going to elucidate more. Even if it doesn't work, you may learn something about the structure of the math, and that's always good. Okay, so I'm not shooting you down. I'm just saying you could go off in different directions. But the way I'm going to phrase it is let's go ahead and just throw that into the definition of the Fourier integral, the Fourier transform. So I have m of t cosine of omega ct. And then I have a kernel, e to the I omega t. And then I'm going to integrate across minus infinity to infinity. And eliminate t. Okay. Now, at first glance, that looks like a mess because I've got function times function times function. But let me rearrange things a little bit. I know something about m of omega. Right? I know something about m of omega, so I'll leave that m of t alone. I've got a complex exponential here, and I've written the cosine as a trig function, and that'll never do. So I can convert that to a trig function, or I can convert that to a complex exponential. And because it's a Sunday afternoon, I feel like converting that to a complex exponential. Now I've got two complex exponentials. So what I'm going to do is combine this guy with this guy. So this multiplied by this gives me an omega plus omega c. You see that? And I'm pretty happy with that guy, so I'm just going to leave that alone. And now I'm going to multiply this guy with this guy. And I have a I omega minus omega c t dt. Okay? Now what comes next takes just a little bit of imagination here. And I can motivate by that saying, okay, I am going to write that as a new omega. For lack of a better symbol, I'll just do omega prime, even though that'll get us into trouble. It won't be too long. Okay? And now if I look at that, I say, well, gee, that's the Fourier transform of capital M of omega prime. right? And now if I look at this guy here and I say, okay, that's omega double prime. It could still be omega prime because it's just a dummy variable. Then this guy here is the Fourier transform of m of t at omega prime, double prime. So this is capital M of omega prime, and this is capital M of omega double prime. And we don't like that omega double prime and omega prime, so let's write that out.
So what you're saying is it's just a sort of a frequency shift.
Exactly right. Exactly right. Remember that a multiplication introduces new frequency components. So what this does is this takes the distribution here and moves it out to the carrier frequencies. It moves it in the frequency space out to the carrier frequencies. So just to summarize, this m of t cosine omega ct, the mixing of the message signal with the carrier signal shifts my frequency content out to omega c, plus omega c and minus omega c. So in the frequency space, here's my signal, m of omega at baseband. And now I have my signal, and it's half as big, right? It's now been shifted out. So the same voice message that I have, whatever that frequency content is, whatever that message is, it now imprints itself at a much higher frequency. And this is what I broadcast over the airwaves. Okay? This is what I broadcast over the airwaves. So all the electromagnetics, all the optics, all those rules now apply to my message signal as it goes down a fiber optic cable or as it dances through the ether or the atmosphere of the Dallas-Fort Worth area. I don't think there is an ether. Thank you, Michelson Morley. Okay? So the way I like to colloquially think about this is if I take some little unsuspecting signal and I mix it with a local oscillator, if I mix it with a local oscillator, I take that frequency component, I take those frequency components, I rip them in half, I throw one to the positive omega c and one out to the negative omega c. So I take this guy, I rip it in half, I throw one to the right, a distance omega c, I throw one to the left, a distance omega c. That's what this multiplication is doing. That's what the modulation is doing. And that's, if you think about it, that's what the modulation property is doing in terms of the convolution.
So the cosine is the carrier.
The cosine is this carrier. That's what the C means. And it comes from a local oscillator.
It's like our waveform generator upstairs.
It's like your waveform generator upstairs. So you're speaking into a microphone. you've got to figure out, one of the things we have to do, and I don't know if we'll have the time to do it today, we might start on it today, but one of the things we have to do is we have to figure out what in our box of tricks, what in our tackle box of electronic circuits will do that operation. I can mimic this operation in a DSP or an FPGA to the extent that I can program a multiplication, but I don't. But in an analog sense, I have to figure out exactly how to do that. Okay, and maybe I'll be able to show you a couple of examples before we quit for the day. But before I do that, let me go through really quickly the architecture of a comm system. Okay. So I have an M of T. I have a transmitter. This is not deep. We will get more complicated, I promise. We have a channel. And then we have a receiver. And so this M of T goes through the transmitter. It's converted into a form that will travel nicely through the channel. It's received and converted back to the message signal. In the case of this modulation, if this is a high frequency, then this message signal is now at a frequency after this modulation where it propagates as an electromagnetic wave over, for example, the airspace of DFW. At the receiver, we have to figure that out. We have to design this. We have to figure out how to do that today and reduce it back down to M of T. Now, a quick digression. What I generally say is this, what I generally want, ideally, whatever comes out of here will be exactly what we send. But in general, we're going to have imperfections here, impairments here, and imperfections there, so that what I get out will be an approximation. So M prime of T is an approximation of M of T. We really want M prime of T to equal M of T. And just a quick word on my notation. The prime is not a derivative. Okay? It's not a derivative. It just means that it's close but no cigar. Or maybe it is exactly this thing. Okay? So I don't know how to emphasize that. Okay? I've confused people in the past about that. It took me a little while to realize I was confusing people. That's really bad. So hopefully by mentioning it, I'm not confusing you. Okay? All right. So this is the general problem. And I've been talking about a channel, and now you finally, after how many hours of listening to me drone along on in comm systems, you now have a building block, a set of building blocks to go with. Okay? So the problem that we just started we have a mixer to shift the frequency up to a carrier, from baseband to a carrier. We'll propagate down a channel, and because this is our very first foray into that, the channel transfer function will just be 1. So no loss, no phase shifts, no nonlinearities, no nothing. The signal just skates right through. On the lab bench, this is called a back-to-back setup. We just put the output directly into the oscilloscope, or in this case, the box that we care about. So even the long BNC cables, there's nothing there. Okay. Lati loves channels that are unity transfer functions. I'll pick on him as the sport demands. So let's walk our signal through the system. The signal here is m of t cosine omega ct. Okay, so if I put my probe there, my voltage probe there, that's what I get. On the output, I get m of t cosine omega ct. And again, that's for a unity transfer function. And so now I need to decide my receiver to get my output m prime of t, which I hope is close to m of t. Now, let's go back to how I cavalierly described this mixing behavior. I took my frequency, ripped it in half, threw one out to the right by omega c, threw the other half out to the left by an amount omega c. That's how I get from that picture to that picture. Okay? So whenever I go through a mixer with a local oscillator like that, it takes whatever the input is, rips it in half, throws it to the right, throws it to the left. Well, I want my m of t to be back around here. I want my m of t to be back around here. So what happens if I come in here with this signal, I rip it in half, throw half to the right, half to the left. The half to the left goes away, it's way high frequency, but the half that I throw to the right, to that direction, goes plunk, right back at baseband. And similarly here, I rip this guy in half, and half of it goes plunk right to baseband, and the other goes to minus omega c. So with that weird, bizarre, unfashionable intuition in mind, let's just see what happens. Let's just see what happens if I do my cosine omega ct local oscillator again, and the input of this is m of t cosine of omega ct here. Okay? Receiver, question mark. A trial run for designing what goes in that box. Okay? If I'm not sure about it, I can try it. I can fish around and try it and guess at the solution. The more I structure my guess, perhaps the more efficient I'm going to be at solving that ill-posed design problem. But at least I have some. I've made some observation, and it could well work. Well, this guy here, this output here, is going to be m of t times cosine of omega ct multiplied by cosine of omega ct. Okay. So that's equal to m of t cosine squared of omega ct. And that's equal to m of t multiplied by 1/2 plus the 1/2 the cosine of twice omega ct. That's trig identity, right?
Right.
That's a trig identity. And if I plot what I'm doing here, then, and I look back at and I see what I've done before, the Fourier transform of this guy here looks like that. I have M of t, half of it. I have M of t, half of it, sitting at the baseband. Really bad picture. Should be nice and centered if my omega c's are perfect. And then half of it at 2 omega c and the other half at minus 2 omega c. Exactly what I said. Rip it up, throw it to the right, throw it to the left, and that's what I get. Very weird description. But that's what the math speaks to me to do.
So is that the most common way of rectifying a signal?
Nope. Nope. I'm not doing any value judgment here. I'm also barely designing a system, right? I'm also barely designing a system. We're just playing around with the modulation property. Okay? Now we are dipping our big toe into the waters of amplitude modulation. I do agree with that. But again, I'm just the purpose of this is not to think too deeply and not to rush right to an answer. The purpose here is just to start to get comfortable with this business of what a mixer is, and show it and do a couple of simple examples, a couple of simple calculations with it. Okay? I don't want to overplay this too much. Okay,
what if you were to multiply by sine of omega c?
Yeah. Well, gee, you'd have to. In fact, that's a great. I think I might have asked that on a test once. We'd go back to this guy here, and we'd have to calculate again what this guy was. And does your intuition tell you something about what that might look like? Here we go. Does your intuition tell you what that might look like?
Yeah, it would look more like that.
It would look like this, but what would be different about it if I used the sign?
It would be an odd parity.
So this I'd have a positive sign here, and this would be negative.
Yes.
That's a pretty good guess. That's a pretty good guess. You might want to double check that. Okay? You might want to double check that. The interesting thing about that is, what if I use both a plus and a minus? If I use both a plus and a minus, I'll have a plus and a plus here, and I'll have a plus and a negative here. And what will happen to those guys here with the opposite signs? They'll cancel. Yeah.
So then you're left with a single set.
Some words like that. Slow. I know you're straightening the tether, but no, slow. Where was I? Okay, yeah. So, but actually, let's see. So, filling in this receiver design here, one piece of this puzzle here is to put one possible receiver design, and there's a million. There's more than one, right? There's many realizations for that receiver design, many different approaches to it. One seems to be to have a multiplier in there, have a mixer in there. But it's not quite there yet, because I still have these frequency components, and I don't want these frequency components there. So I want to get rid of this guy here. I want to keep this guy here. I want to keep, and I want to lose. I want to keep and I want to get rid of this guy here. So how do I sort this guy and unpick that guy? What do I do? Low pass filter. So we want a low pass filter to get rid of the high harmonics. And that means the other half of this guy here is a low pass filter block. So our final system is M of t cosine of omega ct through the channel equal to 1 through a cosine of omega ct there through a low pass filter. And do I get M of t out? Is that the way the bookkeeping worked? Did I get half of it back? So let's see. I started with 1. I put a half over there and a half over there. I threw a quarter back over here. I threw a quarter back over here. Those add to be a half. I lose a quarter at the higher harmonics, so I get 1/2 of M of t back out. So M prime of t equals 1/2 of M of t, which is pretty nice, pretty low level of distortion considering your channel probably has a loss of about 10 to the 5th, 10 to the 6th. Think about taking hundreds of kilowatts or a megawatt and smearing it out over a sphere the size of DFW, right? And then the ratio of a few meters of a ball divided by several hundred kilometers of a ball, the surface areas of those are going to scale by 10 to the 3 orders of magnitude, 6 orders of magnitude. So even if there's no atmospheric loss, no rain or soot or anything like that, you're going to have just a redistribution of energy. Think of a beach ball smeared with, say, an inch of peanut butter. I don't know, for some reason this makes a lot of sense to me. And now you take that beach ball and you make it 100 kilometers diameter, and that inch of peanut butter now has become millimeters of peanut butter. It's just a really smooth scraping of that. Same amount of peanut butter now spread over a much bigger surface. Peanut butter is E cross H.
Interesting.
Okay. Number of things we can do now. One thing that I wanted to okay. Yeah. Time for a little bit of engineering stuff here. Now, whenever you look at this guy here, this was our system that we came up with. We hunted and pecked our way through the system, which is not a bad design approach. And it happens. It's a blending of intuition and analysis. Intuition, guessing, analysis. We had a brand new toy, so we decided to play with that. Found a use for the brand new toy. We guessed at using the brand new toy again, and we came out with one design for a receiver, one design for the back end of the receiver. So we're looking at this and we're pretty happy about this. There's a lot more engineering to be done. But one thing to do is you start to say, what can go wrong? What are the what ifs? And does this work with sines? You came up with that. That's an excellent issue. That's an excellent problem. This guy here is under the control of the radio station, right? So the radio station has control of whether it's a cosine or a sine. Maybe. The radio station has ownership of this part here. The radio station does not have ownership of every single car radio in the DFW airport, in DFW region, right? So this here is where things can get a little dicey. So what are the things that can go wrong on this receiver side?
be out of phase.
Yep. Cosine of omega c t plus some phase angle, theta. What else could go wrong?
Not exactly the same frequency.
Yep. Cosine of omega c, and I'll put my little prime on it to denote that it's not the same. It's not a derivative of that. It's just a prime. It may or may not be close. I could also write this as cosine of omega c plus delta omega t. Right? So here I get differences omega c prime minus omega. Here I just get the delta omega. Those are the same. Channel, what can go wrong with the channel? Attenuation. And in a real life system, that could actually be 10 to the minus 6, not 1. What else could it do? It could encounter noise in the channel. And where we will model that is we'll put it right in there. We'll add the noise right there, because that's where the signal is absolutely at its weakest. What else could the channel do? Attenuation is one thing, and you're talking about attenuation that's flat across all the frequency content at omega c, right? Is that the only thing that can happen? So there could be filtering effects. Multipass. Certain frequencies attenuated more than others. Phase shifts. Okay. So I could model this. I could model that filter as some horrible filtering function. Right? This is a signal that goes through this box. The box can attenuate some amplitudes, some frequency components more than others. It can wiggle the phases around some frequencies more than others. So we can model that whole thing, that whole channel as a filter. If we know that transfer function of the filter, maybe we can do something on the back end to fix it. And we'll actually do that. One of my lectures to come will actually do exactly that. Okay? Lati does the same mathematics and calls it vestigial sideband, which is fine, but it's a ridiculous use of the mathematics. So we'll do the same thing. We'll do the same thing, but we'll do it for what I think is a more pertinent problem. Filters are linear, time invariant. So what else could happen in that channel?
Time shifting.
Time shifting would be a phase delay.
Okay.
Time shifting is a phase delay if I normalize every time shift to a frequency. Right? I'll harp on that again over the course of the semester. I find it easier to consider group delays instead of phases, and one is the derivative of the other. Right? So if you think about your filter response, we always teach you about phase response. I find phase to be rather difficult to wrap my brain around because the phase, the number of radians, is pegged to a particular frequency. And so if I'm treating a large number of frequencies, I'd rather know this frequency component was delayed 7 nanoseconds, this was delayed 3 nanoseconds, this was delayed 6 nanoseconds. That to me makes more sense than the relative phases of all of those. But your mileage may vary. Okay? So that'll roll up into filtering effects. It's hard to imagine this with airspace But if this channel had material in it, like a fiber, and to give you an idea, the core of a fiber is 9 microns diameter. So where the light is in a fiber is 9 microns. Okay? The average power is about a milliwatt. But milliwatt, focused in time, focused down to 9 microns of diameter, is a tremendous amount of power. And then you might have 160 channels in that fiber at once. So there's a tremendous amount of light power in that 9 microns, and you might stay in that fiber for 9 megameters, which is a heck of a lot of molecules to tickle. And a heck of a lot of molecules to tickle, not in a linear sense, but in a nonlinear sense. And so in some, if this is linear, there's also some nonlinear impairments. Okay? So in many systems, there's nonlinear impairments. So one of the things that we'll harp on, one of the things we'll do is we'll get our design, and then we'll ask ourselves we'll be good paranoid engineers. A good engineer is also paranoid, and we'll do this exercise of what things can go wrong with this design. Okay. Now, if you look at it, each of these problems. A lot of these problems you guys can solve right tonight. The sign, you almost already guessed it, right? You just have a little bit of mathematics to do to button that up. Similarly, if I have a phase shift in here, it's not too big a stretch to go back through the mathematics of the low-pass filter and add that phase shift in there and carry that phase shift along. It's really just an extra trig identity. And similarly, these effects. And similarly, we've been talking at great length about filtering, including the beginning of this class, and so you've got your toolkit ready for that to go as well. Noise, you need some help on that. Noise will need some help on that. But I'll be here for that. I'll try to earn my money on that one. The rest of it, I'm just going to be a guide, but that one I'll be a little bit better. And nonlinear impairments, maybe you'll struggle a bit at first, but that you'll pick that up with just a little bit of a boost as well. Okay. And the other thing, so what I'll point out is all the stuff in red. That's all the stuff that homework problems, that test problems come from. Okay. So I'm always thinking about where certain impairments can happen, and what are ones that you can explore in say 15 minutes on a test. Okay. And so if you want to start getting into my weird warped mind, that's a good way to start doing that. Okay. Now we have a lot of we still have a lot of stuff to go with AM. We did a tremendous amount just here to get us started. That's fine. We have a lot more cases to go over in a little bit more detail. The other thing that I don't have time to talk about today, so you'll have to wait till I get back, is exactly what we mean by this element here. Okay? You're very forgiving because you're letting me do all this mathematics. You're patting yourself on the back by saying we have a full system. We can put in an MFT and we can get out an MFT. You're pretty happy with even the argument, I think, of why we want to move from baseband to a carrier. But we have no earthly idea. We have no earthly idea what that box looks like.
You mean the hardware behind that box?
Absolutely. We don't know what the hardware is behind that little circle with the X in it. So at this stage, I'll humble you a little bit by saying, well, How do we realize it? Okay? And so that's going to be the subject of my next lecture. You'll hope that I come back, because otherwise you'll never know what's in that little circle with the X in it. And what I'll do is I'll walk you through some nice examples, both in the optical world and in the electronic world. And the optical world, as I pointed out, is it's hidden from your purview, because you're always carrying around a cell phone, and you're very attuned to the wireless side of the house. But I'll point out that at any instant in history, even at the big photonics bust right around the turn of the century, the spending in the photonics world, the spending in the fiber optics world, was at least twice what it was in the wireless world. Okay? And these are the backbones that connect city to city to city, across the Atlantic, across the Pacific, that really span continents. Okay? So I'll start with the optics side, because it's actually a little bit easier to see, to realize that modulator, simply understand how those work. And then I'll move into some examples from the electronic side of the house. Okay? All right. With that, I will quit. It's flashing, so there's still about 5 minutes of recording time. If there's any questions of things from the weekend, I'll be happy to listen. I'll try to then answer them.
So for unit assignment, is that inverted?
Well, this is a phase-shifted cosine.
Yeah.
What we would do is, we sort of guessed at what it might be in terms of the flipped negative frequency, because that's the phase issue. But what we'd really want to do is we'd really want M of t multiplied by that, and we'd want to walk through the system to see what happens. And in fact, that is something that we'll do. In fact, what we'll do is we'll take one message signal and encode it on a cosine, and another message signal, a second message signal encoded on a sine. And what we'll do is we'll show that they can share the same channel because they're 90 degrees out of phase, and we can separate them out or demux them out at the receiving end. Okay? But we have to. But don't believe me. Wait for me to prove the math. Okay? I will motivate it by saying this link, this antenna, very expensive. The bandwidth we bought from the FCC, very expensive. If I can get twice the information down that channel, I get twice the revenue. Good. Right? For a little bit more hardware, an extra local oscillator, a few extra amplifiers more, if I can share the same antenna, share the same channels, and get twice the revenue for a little bit of extra fixed cost, I'll do that all day long. Okay? So that's one of the motivations, is how do we get more information through there? That's the engineering way of putting it. How do we milk more money from our assets? That's the financial way of looking at it. Okay?